Hello, chemists. So, welcome to Chapter 3, where we will be talking about composition of substances and solutions. This might be a good time to mention that midterm 1 will cover chapters 1 through 3, so including this chapter. So this chapter is much more calculation based. We'll be doing a lot of math manipulation. So let's hold on to our non-graphing calculators in one hand and then our periodic table in the other hand, and then let's get started. All right, so just an overview of the chapter. In the first half of the chapter, we will be looking at formula masses, molar masses of different substances based upon their chemical formula. And, we've talked about ionic and molecular formulas in chapter 2. So now we will be using those formulas in conjunction with the periodic table for use in calculations and dimensional analysis. Then in the second half of the chapter, we will look at composition of solutions, namely concentration of solutions. So that's, a homogeneous mixture. And we'll use those concentrations in other types of liquid phase calculations. All right, so now let's get started. Okay, so we introduced atomic mass, masses of single atoms based upon the periodic table, those atomic weights that you get off of our periodic table. All right, so once we put together a bunch of atoms in a certain arrangement, we can calculate a molecular weight of a molecule. So this is namely for molecular compounds that are only composed of nonmetals. So to calculate a molecular weight of a molecule, essentially you just take the summation of all of the atomic weights of that particular compound. So as the chemical formula is written out. So let's do this definition. The molecular weight or molecular mass of a substance is the sum of all of the atomic masses of the atoms in the molecule. So you really need to look at the chemical formula for whatever that molecule is. Chemical formula. That will tell you exactly, formula. That will tell you the number of atoms that are composed in that substance, in that molecule. So let's just do an example to get the molecular weight of ethanol. So ethanol has this chemical formula, C2H6OH. So to calculate a molecular weight, we need to take inventory of all the atoms that are in the chemical formula. So let's take inventory. So there are carbons, there are hydrogens, and then there are oxygens in this molecular compound. It's all nonmetals. So I see that there are two, so we're looking at the subscripts now. There are 2 carbons within this compound. There are 5 hydrogens, H5, but then there's also another hydrogen tacked on to the end here. So we could also rewrite this formula as C2H6O, but the reason chemists write it this way is to convey some of the structure of ethanol, which we talked about in chapter 1, or I think, no, chapter 2, about how to convey structure within a formula. So anyway, back to ethanol. In this chemical formula, there are 2 carbons, a total of 6 hydrogens because of the one tacked on at the end, and then there is only 1 oxygen. So with each of those atoms, they all have a specific atomic weight as indicated on the periodic table. So now we will use our periodic table and associate those atomic masses with the correct atom and take into account how many of each atom there are. So since there are 2 carbons, we're going to do 2 times the atomic weight of carbon, so that's 12.01 AMU. There are 6 hydrogens, so 6 times the atomic weight of hydrogen, which is 1.008 AMU. And then finally, just 1 oxygen, so oxygen is 16.00 AMU. All right, and then all you do is add them up. All right, and so if you add them up, you get 46.08 AMU. And so if we want to think about significant figures here, this is an addition problem. So these 2s and 6s, these are counting numbers, so that does not affect our number of significant figures in these values. So essentially, it's just an addition problem. And remember, with addition problems, we always look at the leftmost significant the leftmost significant place of all of the values. So in my mind, I think, okay, 12.01 ends in the hundredths place, 1.008 ends in the thousandths, and then 16.00 ends in the hundredths place. So our answer should be rounded at the hundredths place. So that's why our answer here is 46.08 AMU. So this is the molecular mass or molecular weight of ethanol. So C2H5O6. So that is how much one molecule of ethanol would weigh in AMU. And so, we talked about our atomic mass units and how that can be translated or converted into a gram amount that we could measure in lab. But remember, an AMU is very, very, very small. 1 AMU equals 1.6737 times 10 to the negative 24 grams. So this weight is very, very small. The weight of one ethanol molecule is very little. We actually couldn't weigh one molecule of ethanol in our lab. Typically, we work with a collection of ethanol molecules in a sample of ethanol, and then we will. So once we start talking about the concept of the mole, I will show you how we can take this number and apply it to a larger sample. So there's a little intro for you. All right, so the term molecular weight and what we did right here in taking inventory of all of the atoms and the atomic weights to calculate this molecular weight applies to molecules that are bonded covalently and are only composed of nonmetals. So we can also talk about weights of ionic compounds, so compounds that are made out of a metal and a nonmetal. Ionic compounds are composed of a cation, the metal, and an anion from the nonmetal. They come together through electrostatic interactions. So we can calculate the masses of one formula unit of an ionic compound. And so that brings us to formula weights. So formula weights is essentially the same as a molecular weight. It's just applied to ions or ionic compounds. So essentially, the definition is the same here. The formula weight is the sum of all the atomic weights in a chemical formula for an ionic compound in one formula unit. In one formula unit of that substance. So, for example, we have sodium chloride. That is the simplest way we can convey the ratio between sodium ions and chloride ions. So this would be one formula unit. And so to calculate the formula weight of sodium chloride is the same way we did molecular weights. So we do the strategy here if we want to calculate the formula weight of copper 2 nitrate, which I have the chemical formula here. It's the same. We take inventory of all of the atoms. So it's this exact same method. So let's look at all the atoms here. There are coppers, there are nitrogens, and then there are oxygens. But now we need to inspect the chemical formula and determine how many of each atom are there. So copper, it looks like there's just one. Nitrogen, so if we look at this, there are 2 nitrate anions. So total, if we look, there's 2 of them. Total, there are 2 nitrogens here. So 2 nitrogens because of that 2 subscript in parentheses around the whole nitrate anion, that polyatomic. And then if we think about the same thing with oxygen, so oxygen, essentially we're applying this 2 multiplier to the whole nitrate anion, polyatomic anion, so there's a total of 6 oxygens there. 6 oxygens. All right, and so it's the same thing. We apply or we relate the respective atomic masses off of the periodic table and add them up. So let's do that. So the atomic weight of copper is 63.55 AMU. That's just straight off the periodic table. There's only one of them. There's 2 nitrogens, so that's 14.01 AMU. and then there are 6 oxygens. So oxygen is 16.00 AMU. And then all we do is add those numbers up. And again, if we inspect significant figures here, all these numbers end in the hundredths place, so our answer should be rounded at the hundredths place. So if we add all of this together, we get a formula weight, because this is an ionic compound, as 187.57 AMU. So this is the formula weight of copper 2 nitrate. And essentially, remember how we write copper 2 nitrate here, this is 1 formula unit, because that's what formula weight is. It's the mass of 1 formula unit of that ionic compound, 1 formula unit. And again, it's the same process to calculate formula weights and molecular weights from covalent or molecular compounds. All right, so when given a chemical formula, whether it be molecular or ionic, as long as you have the periodic table, you can figure out how much one of those molecules or one of those formula units will weigh in AMU. Okay, so what else can we do with the periodic table and these atomic weights, formula weights, molecular weights? We can calculate the percent composition of certain atoms in a compound. So what is percent composition? Percent composition is the percent by mass of each element present in a chemical formula, or in 1 unit of that compound. Each element present in, go back to green, in 1 unit of that compound. So we need to know the molecular formula, or the chemical formula for the substance, and we can calculate the percent composition of one of the elements or all of the elements in that sample. If we add up all the percent compositions of all of the elements, we should get 100. All right, and so in order to calculate percent composition, you need to know the chemical formula. So the ratio, that'll tell you the ratio of atoms, and the mass of each atom type, which we can get from the periodic table. And so here's just the formula to get it. But I think once you see the process, it'll be pretty straightforward. But the equation here is the percent mass, or the percent composition. This is our percent composition of any element in a compound, is the mass of that element that's in the formula divided by the total mass of the formula. So that's the molecular or the formula weight, formula mass of that compound, and then multiply by 100 to turn that into a percentage. So let's do a problem, because I think it's easier to show it that way. So let's find the percent composition of chromium, nitrogen, and oxygen in a sample of chromium nitrate. So I have the chemical formula here of chromium nitrate. So our strategy here is to first find the formula weight of this ionic compound. So it's the same steps we did in the previous slide. So let's take inventory of all of the atoms within this chemical formula. So there's chromium present, there's nitrogen, and there's oxygen. So there's only 1 chromium. We look at nitrogen, so there's 3 nitrate anions present. So there's a total of 3 nitrogens. So we'll have to take that into account when we calculate or apply those atomic weights of chromium, nitrogen, and oxygen. And then oxygen, how many oxygens are there? Since there's that 3 subscript, we do 3 times 3, so there's a total of 9 oxygens present in this chemical formula. Again, I'm doing the same work as I did before. Now that I've taken inventory of all those atoms, I will look at the periodic table and those atomic weights that are listed here. So I see that there's 1 chromium, and chromium has an atomic weight of 52.00 AMU. Nitrogen, there's 3 of them, and so 3 times 14.01 AMU, and then there's 9 oxygens, so 16.00 AMU. And remember, since our goal here is to calculate percent composition, it's the percent by mass of every element. Remember, AMU is a unit of mass. Remember how up here we related it? It's a tiny, tiny fraction of a gram. So AMU is a unit of mass. Okay, so I've taken inventory of all these elements. I can go ahead and add them up. But a nice way to save yourself some time is do the math here for each line. Essentially, what is the mass of all of the chromium? What is the mass of all of the nitrogen? What is the mass of all of the oxygen? This will save us a little step when we get to those, when we apply the percent composition formula, because here in the numerator, we put mass of each element in the formula. So we find the weight of all of the chromium. We know that that weighs 52.00 AMU. I'll move this. Whoops. Move that over there. This is for chromium. And then if we do the same thing for all of the nitrogens, that is equal to 42.03 AMU. That's how much all of the nitrogens weigh. And we do oxygen, which is 144.00 AMU. That's all the oxygen. All right? And then go ahead and add all those numbers up to get the whole formula weight of all of the chromiums, nitrogens, and oxygens in the chemical formula. So that will give you a number of 238.03 AMU. So this is our formula weight. That's our formula weight. And then these three numbers are essentially the components, the weight of all of the three components. So let's figure out what percentage of this total formula weight is chromium, what percentage is nitrogen, what percentage is oxygen, and take into account significant figures here. I'll note when we added all of these up, they all end in the hundredths place, so that's why my answer ends in the hundredths place. So you see we actually gained some significant figures because our answer is above 100. So we have 5 significant figures here. And so take note of that as we calculate our percentages. So I should give myself another, I'm just going to give myself another page for a little bit more room. Okay, so to get our percentages, or percent compositions, so percent composition by mass of chromium will be equal to the mass of chromium divided by the mass of the whole compound, which is chromium nitrate, times 100% to turn that into a percentage. So if we do that, let's look at the numbers that we just calculated up here. Note how I saved myself a little bit of time. So all we will do to get the percent composition of chromium is do 52.00 divided by our formula weight times 100 to get that percentage. 52.00 AMU, that's our mass of all of the chromium. So I'll say all chromium, but in this case there's only one atom. And then the mass of chromium nitrate, which we just calculated, is 238.03 AMU times 100 to turn that into a percent, and we get 21.85% chromium. That's the percent composition of chromium by mass in chromium-3 nitrate. And let's take a look at significant figures here. So we see the numerator only has 4 sig figs, while the denominator has 5 sig figs. So that's why our answer here has 4 sig figs, because we are limited by 4 sig figs in the numerator. All right, so let's do the same thing for nitrogen. So let's do percent composition of nitrogen. It's the mass of all the nitrogen over mass of the whole compound, chromium nitrate, times 100. So let's take a look back up here. So the mass of all the nitrogen is 42.03 AMU. So 43.03 AMU over the total mass, 238.03 AMU times 100 equals, let's see, 17.66%. That's of nitrogen, percent nitrogen in this in this substance. Again, look at significant figures. Our numerator has 4 sig figs. Our denominator has 5. We're limited by 4 sig figs in the numerator, so our answer should have be rounded to 4 sig figs. All right, lastly, oxygen. So hopefully you see the pattern here. Percent oxygen, it's the mass of all of the oxygen over the formula weight of the whole chemical compound times 100. So in this case, it's 144.00 AMU over the total mass, which is 238.03 AMU times 100 equals, let's take a look at significant figures before I crunch those numbers. So 144.00. So note here, when I took 9 times 16.00, 9 has an infinite number of sig figs. It's a counting number. So our answer here should end at the same place as what 16.00 has to, so to the hundredths place. So 144.00 is the correct number of significant figures for all of the mass of oxygen. So that number has 5 significant figures, and our denominator also has 5. So our answer, when we convert that into percentage, should also have 5 significant figures. So our answer, crunch those numbers, is 60.497% oxygen. All right. So those are percentages for the chromium, nitrogen, and oxygen within a formula unit of chromium nitrate. And then you can always check yourself if you calculate the percent composition of all of the elements, it should add up to 100%. It'll be pretty close to 100% because we do have an extra decimal place in the oxygen calculation, but that's because of significant figures, but it should be very, very, very close to 100%. So that is how you calculate percent composition. All you need is a periodic table and the chemical formula of that substance, and you can calculate the percent composition of any element in that chemical formula. Okay, so in all of this percent composition work, formula weight, molecular weight, we calculated these values off of using the periodic table while applying the unit AMU to those values off of the periodic table. We said that AMU is very, very, very small. AMU is what we said, it's 1.6737 times 10 to the negative 24 grams. I don't know about you, but I don't have a grasp of how much that is. I just know it's very, very small. So how can we weigh out molecules, elements in a lab setting, a more realistic setting? And that's where the mole comes into play. So we need to be able to translate the information off of the periodic table and chemical formulas to something that we can use. Essentially, we're moving away from just talking about singular atoms or a collection of atoms. We're talking about larger samples that we can use. When I say practically use, I mean how can we use this in lab or in a more realistic setting. So this is where the mole comes in. The mole is just a number. Just like when we say a dozen, 1 dozen equals 12 of something, like a counting number. Same thing with a mole. A mole is just a number. So the reason we use a mole, and we essentially scale up our atoms to a more realistic number that we can actually weigh, is because the AMU is too small, and we've already said that AMU is very, very tiny. I don't know about you, I don't have a grasp of how much that weighs. Like if I have a sample of something, I can't be like, yeah, that's like 5 AMU or something. No, I don't know. So that's why we use a mole. And so another reason we use a mole is because it's easier to talk about a collection of atoms instead of singular atoms, instead of individual atoms. So kind of like eggs, it's easier to think about buying eggs in units of a dozen, right? We talk about a dozen of something, that's 12. So when we talk about a mole of atoms, like a mole of carbon atoms, we're talking about a collection of those atoms. And so I have some cute pictures of moles, Hans Moleman, that mole guy from I think the first and second Incredibles movies. And here's the American Chemical Society, their mascot, the mole. Yeah, he's wearing safety goggles. That's cute. Okay, so what is that number? I told you a mole is a number. So what is that number? So like a dozen is 12, a mole is equal to Avogadro's number, which is equal to 6.022 times 10 to the 23. Right? So like 1 dozen equals 12. A mole is equal to 6.022 times 10 to the 23 of anything. So that's a mole. So that number was named after Amadeo Avogadro. So he came up with a way to talk about elements and atoms in a collection so we could actually measure them in lab. And so when we're talking about a mole of a substance, we're talking about a large collection, essentially 6.022 times 10 to the 23 of that element. And so the reason we use this number, this specific number, is because the numbers on the periodic table don't change. So, like when we were talking about the atomic mass of carbon is 12.01 AMU. When we talk about a mole of carbon, that number stays the same, but now we're talking about grams. So 1 mole of carbon equals 12.01 grams. And that's where the definition comes from, essentially. So this Avogadro's number comes from the definition that's the number of atoms in a carbon-12 sample that is exactly 12 grams. So it's a way we can scale up that AMU unit to a more practical unit, and so now we can actually work in grams. All right, and so yeah, the number of atoms or of anything is called a mole. So just like we say 1 dozen equals 12 particles, it's the same way we can relate those two numbers. And so you see here, 1 dozen equals 12 particles, or 1 mole equals 6.022 times 10 to the 23 particles. These are our equalities that we can use in conversion factors within dimensional analysis, which I think I show you. No, not quite. Not quite. But we can use these equalities in dimensional analysis to convert between moles of a substance to individual particles of that substance, or we can convert between a dozen of something to number of particles or number of items within that sample. Okay, so I kind of gave you a glimpse of the significance of the mole and why we use it. So just a reminder, 1 mole of any atoms has a mass in grams that is equivalent to its atomic weight in AMU. So this is called the molar mass. It's how much 1 mole of that substance weighs. And so if we look at the numbers off of the periodic table, each of those numbers, the atomic weights, can tell us 2 things. So all those numbers on the periodic table tell us 2 things. It can tell you the average mass of 1 atom of that element, which we've been doing up until this point. So that has a unit of AMU. So essentially like AMU per atom, each of those numbers. So like, for example, oxygen is 16.00. We know oxygen is 16.00 AMU for 1 atom, but it also tells us the mass of 1 mole of that element. But it has a different unit, but the number is the same. So this will tell us a gram amount per mole. So that means oxygen, 1 atom of oxygen is 16.00 AMU. So how the mole is related to the periodic table, 16.00 is also the weight in grams for 1 mole of oxygen. And so this value also ends up being a conversion factor or a quality that we can use in dimensional analysis. So that number becomes an equality, 16.00 grams equals 1 mole of oxygen. And so we will use that within our dimensional analysis calculations in the rest of this chapter. And so you can use any one of the masses on the periodic table to make that relationship. So oxygen just so happens to be 1 mole of oxygen will weigh exactly 16.00 grams, or neon, 1 mole of neon will equal 20.18 grams. So those atomic masses, or sorry, those numbers, the atomic weights listed on the periodic table can tell us two things: the mass of one atom in AMU of that element, or the mass of 1 mole of that element in grams. We will mostly be using the second one because we are humans living on Earth, where we can only measure things really in grams. I don't have an instrument that can measure stuff single atoms in AMU. I do have balances and scales that can measure in grams, so we will mostly be using this second way to read the periodic table in grams per mole. That, like titanium, 1 mole of titanium will weigh 47.88 grams. All right, so keep that in mind. So again, the mole, we use this to convert from the atomic scale that we have been talking about, single atoms, to the laboratory scale. So here's another example. If we calculated the atomic mass, or the molecular mass of 1 molecule of H2O, if we calculated that in AMU, you would see that there's 2 hydrogens, 1 oxygen, and you would calculate that equals 18.002 AMU. But we can't measure an AMU in lab. So that's why instead of talking about single molecules of water, we talk about moles of water. So if we apply Avogadro's number, and instead of talking about 1 molecule, let's talk about 16.022 times 10 to the 23 water molecules, instead of 18.0 AMU, this collection of molecules, a mole's worth of water molecules, actually weighs 18.0 grams. And so see how those numbers are the same, it's just the unit is different. You and we can measure 18 grams or 18.02 grams in lab. And so that's why the mole, the concept of the mole, is very important. And so why does this work? When applying the mole, instead of talking about single atoms, talking about moles of atoms, why does that number on the periodic table, why does it not change? It works because it takes exactly 1 mole of the atomic mass in AMU to make 1 gram of a substance. So that's why that number that the mole is, 6.022 times 10 to the 23, is such an important number, and has been calculated to be that number in order to convert AMU to grams in a very direct way. All right, so let's do some practice problems that practice using our definition of a mole, Avogadro's number, where 1 mole equals 6.022 times 10 to the 23 particles of anything. All right, so this first problem: how many moles of potassium are contained in a 250.0 gram block of potassium? So I give you the atomic weight. This is the same number that's on the periodic table for potassium right here. I give you a couple more significant figures in this number. So remember, we said atomic weight, that has the unit of AMU. So this means 1 atom of potassium equals 39.098 AMU. But remember, that number also means molar mass, the mass of 1 mole of potassium. So that means atomic weight is the same number as molar mass, but just a different unit. So this also means that potassium is 39.098 grams of 1 mole. So that is equal to 1 mole of potassium. So this number in AMU is when we talk about single atoms. We use this number with the gram unit, 39.098 grams, when talking about a mole's worth of potassium. All right, and so since this problem is asking for moles of potassium, we want to use this equality in a calculation. So if we start with the number that's given here, 250.0 grams, 250.0 grams of potassium, And this is our goal. We want to know how many moles of potassium there are. We can see if we use the molar mass definition, the molar mass equality for potassium, this number relates the number of grams that are contained in 1 mole of potassium. So we can relate mass in grams to moles. So we can use this equality within our dimensional analysis setup. Right now, I'm in the unit of grams of potassium. So I can put this number, the 39.098 grams of potassium, on the bottom of our setup. So 39.098 grams of potassium. And then I put the other part in the numerator. And so you can see that grams of potassium cancel, leaving us with the unit of moles of potassium. And that's what we want. So then we just stick that into our calculator and get a number 6.39418 moles of potassium. But remember, we always inspect significant figures. So if we look at these numbers, 25.0, or sorry, 250.0, this has 4 sig figs. 39.098, that has 5 sig figs. And this 1 mole of potassium, this has infinite number of sig figs. It's like 1.00000. It's like a counting number. So our answer will be limited by 4 sig figs in the 250.0. So I want to round my number to 4 sig figs, so 6.394 moles of potassium are contained in a 250 pound or gram block of potassium. And yep, that's the answer given right there. All right, so this showed how to use the periodic table, the number given for an element in grams per mole, and use that in a dimensional analysis setup. So I'll just also point out this atomic weight. When instead of using it in AMU, we can say it's 39.098 grams per mole of potassium. So see our grams per mole unit here, that's kind of like a derived unit, and that's how I got this equality. That 39.098 goes with the grams of potassium on one side, and then since mole is on the denominator, it gets an implied 1 attached to it. And that's exactly how I got from this number to that equality to use within this dimensional analysis work. And again, if you do it this way, if you think about creating equalities, you don't have to think about, oh, do I have to divide or multiply by atomic mass, atomic weight to get to moles? You don't have to think about it. You just have to move the units and numbers around to get the unit of the answer you want. Okay, so let's do a second problem here. What is the average mass in grams of a single potassium atom? So we want average mass in grams. All right, and so we're going to use the periodic table to our advantage here. So again, I can just kind of rewrite this equality. 39.098 grams of potassium is the weight of 1 mole of potassium. So that is the average weight of 1 mole of potassium is 39.098 grams. But we want the mass of a single potassium atom. So here, the hint is look at the units. Our goal is to get the unit of grams per atom because we want the mass of 1 potassium atom. So if our goal is to get to grams per atom, if we start with the molar mass on the periodic table, that has a unit of grams per mole. So our goal is to convert mole into atoms. Thankfully, we can use Avogadro's number. We know that 1 mole of anything equals 6.022 times 10 to the 23 particles, or in this case, atoms. So this is an example of using Avogadro's number in a calculation to convert from moles of a substance to atoms of that substance. So if we do that, so we're going to use this equality and convert the denominator. So we want to convert moles to single atoms. So I'm going to put 1 mole up top here, and then 6.022 times 10 to the 23 atoms on the bottom. Doing it this way, you'll see that moles cancel, and then we're left with atoms on the denominator. So then in the end, our answer will be in grams per atom, and that was our goal. We want to aim to get to grams per atom, or the average mass of one atom of potassium. And so if we stick that into our calculators, which I will just show how to do, just to kind of remind you how to put large numbers in scientific notation into your calculator. So I'll just remind you, in your calculator, you can put this number in as 6.022 E23, but you see that it's division. So how I'm going to put this in my calculator is, you don't have to like put parentheses around each one, do each calculation separately and multiply them all together. Remember the rules of multiplication and division. You can do them in any order that you want. Multiplication and division, you can do them in any order. So essentially what I'm going to put into my calculator, I'm going to put 39.098 and then divided by 6.022 times, or e to the 23, because 39.098 over 1, that's the same number. I can just essentially ignore these ones. I don't have to put them in my calculator. Divided by 1 times 1, it's the same number. So instead, I'm going to just put 39.098 into my calculator. All right. Times 1, I don't have to do. Divided by 1, you don't have to do. But then you have to divide by 6.022 E23. So I'm just going to essentially put that in my calculator, 6.022 E23. So that's what I have in my calculator. Right? So you don't have to like put 1 over 6.022 times 10 to the 23. You can just simply do divided by 6.022 times 10 to the 23 because it's on the denominator. There are some just tips for you to work through calculations on your calculator a bit faster. And I will point out, some students will think you can just to do this, you can like multiply by 6.022 times 10 to the negative 23. You can't do that, so don't do that. Anyway, so all I'm putting into my calculator is 39.098 divided by 6.022 e to the 23, and then you get, out of your calculator, you get a number 6.4925 times 10 to the negative 23. And so that unit is grams per atom. So let's look at significant figures. Don't think that I forgot. So in this case, Avogadro's number only has 4 significant figures, while 39.098 has 5. So our answer will be limited by 4 sig figs. I'm going to round right here. So our answer is 6.493 times 10 to the negative 23 grams per atom. That's the average mass of one atom of potassium. Right? So that number, I mean, I don't know about you, but I don't know how much that weighs. It's really, really tiny. Again, it's easier to work in moles of substances when we're in lab, but in some calculations, we'll have to convert to atoms. So that's why knowing Avogadro's number to relate moles of a substance to atoms of a substance is important, because the mole is a bridge between the atomic realm, or like microscopic realm, or domain, microscopic domain, to our macroscopic domain. Essentially lab-based things that we can touch, things that we can hold. The mole is the bridge to talk about, instead of talking about singular individual atoms and molecules, how can we talk about samples in a number that we can actually hold? So again, you can use the mole and Avogadro's number to go from particles to grams of a substance, or you can use the mole to go from grams of a substance to particles of a substance. Again, that mole, our Avogadro's number, which everyone should know, 1 mole equals 6.022 times 10 to the 23 of anything. So let's just say particles, whether it's molecules, atoms, whatever, helps us make that bridge between the microscopic and macroscopic worlds. All right. And so this table kind of just emphasizes the how to use the periodic table in terms of AMU when talking about single formula units, single atoms, and how that's the same number when calculating molar mass. Essentially, how much does 1 mole's worth of atomic nitrogen weigh? All right, and I'll take a note here. If you look at silver, so here, the formula for silver, it's an element. The formula weight straight off of the periodic table is 107.9 AMU, and its molar mass is 107.9 grams per 1 mole of silver. Here you see silver ion. Silver has a fixed charge. When it's an ion or cation, it always forms silver plus. And so there's a difference between of 1 electron. So silver, neutral silver, will lose 1 electron to make a silver ion. So you see here that the formula weight for that ion is essentially the same, whether you're talking about a neutral silver atom or a silver ion, a silver cation. This is due because electrons have a very, 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 very small mass. It's negligible. So ions and atoms essentially have the same mass for our purposes here. So again, when we're calculating the ionic the formula weights of substances, you can just use the neutral masses of the atomic weights on the periodic table. So you can essentially just ignore the charges when calculating those things. All right, and so I just wanted to point that out, that you're using the same masses, whether it's neutral or it's an ion. All right. Okay, so that kind of goes over formula weights, molecular weights, and the mole, and how we can use molar masses in our calculations. We'll do a lot more practice as the semester goes on. All right, and so stick around and we'll talk about empirical formulas and how to calculate them.